Welcome to UV Physics Academy. So here we are discussing Grover's algorithm. So in this third part, we are going to discuss about the circuit design of Grover's algorithm. So Grover's algorithm contains a total three operations. First one, superposition of 0 to n minus 1 states, and the next inversion operator which invert the amplitude of target state, and the next one is diffusion operator. Okay, so first let us discuss about this superposition. So how to create this superposition state? I hope everybody know. So for example, here we have n number of qubits. Let us say they are in the 0 state, and here we have Hadamard gates. H tens are n. That means n number of Hadamard gates are operating. So this will create the superposition of the states, summation x, and here x is equal to 0 to n minus 1, where this is 1 over root n is the normalization constant. So that's it, and this is the superposition of the states 0 to n minus 1. Okay, fine. And this will we will split into target state and remaining states. I hope you know this also. So here we can write this as alpha naught summation remaining states, and here a beta naught into target. So here r is not equal to t, and we are taking this as initial state psi naught, which is a superposition state. Okay, that's it, where alpha naught and beta naught equal to 1 over root n. That's it. And the next one is about inversion operator. Okay, so what is this inversion operator? So with the help of this operator, we can invert the amplitude of target state. So the operator form is t for target. Okay, this is equal to I identity minus 2 into the outer product of t. Okay, so target state, outer product of target state. That's it. And how to create this, how to construct the oracle? Okay, so here I'm considering a 2 qubit example. First one, so 2 qubits example. So let us suppose the target state is I'm assuming it as a 0 0. That means in a decimal state notation I can write this as uh, 0 2 qubits. This is my target state. How to create an oracle which invert the amplitude of only that 0 state? Okay, so for this I'm taking the help of uh, 2 qubits are there, that's why I'm taking this. Okay, so here we have control jet gate, right? Okay, so here the state is 0 0, target state is 0 0. So here we have 0, this one LSB. So add one X gate this side as well as this side. Wherever 0 is there, you just add this poly X gate. And this is nothing but this, we can write it as this is nothing but anti-control. So here this is the control, okay, and here is the anti-control, because X control and again X is nothing but anti-control. So what is this anti-control? Actually, if that generally control operation is if that control bit is 1, then only that operation, that unitary operation occurs. Here anti-control, if it is a 0, then only that operation occurs, something like that. I have already explained these operations in the quantum circuits. I request you please watch that. So this is anti-control, and here one small thing I want to discuss. If you observe carefully, this is XZX. So I would like to discuss one thing, that is, whenever you have x, Pauli x, and here we have one matrix, let us say A, B, C, D, and again x. Very simple multiplication. What you have to do is, uh, this Pauli x will interchange rows, and this x from right side, it will interchange columns. Okay, so then finally what will happen, this matrix, the diagonal elements will interchange. That means here we will get D, here A, and A and D are interchange, and B and C are interchange. So here C and here B. That's it. So here I am taking, instead of Z, I am taking one unitary operation. Don't forget this anti-control. And I hope you know what is a Z. 1 0 0 minus 1, 1 0 0 minus 1. So that's why minus 1 come here, 0 0 1. Okay, that's it. And I told you already, the first column stands for off and the second column is for on. And here it is 1 and here it is 2. Okay, so then finally this is anti-control, that means a 0. So that's why that unitary operation u of 0 comma 1. This decimal state notation I have already explained in the quantum circuit, how to solve any quantum circuit by using a decimal state notation easily. So you feel that is a little bit lengthy, but once you understand this, this is a very straightforward and it very easy. And here it is off and on. So carefully observe. This first column stands for off, second column stands for on. That's why the 0 state become minus 0. That's it. Still not understanding? No problem. Let us take one more. So here I am taking the target state as a 1. Okay. So in the decimal state notation, I can write it as a 1 with the 2 qubits. Right. So let me take the circuit, oracle here. So here I have LSB. This is a 1. Okay. So that's why, as usual, first let me take the control Z gate. And after that, uh, here the first one is 1. That's why no Pauli X gate. But here it is a 0. So that's why here 0. Okay. So then this is nothing but, here we have X control X. X control X is nothing but anti-control. And after that, this Z gate is as usual. So what is this operation? Z of anti-control, no need to consider 1 and a 2. So if this is a 0, then only it will operate. That operation will execute. So that means Z 0 comma 1. Okay. So that's it. I have already explained in that video. I request you please watch. And a 0 off, 1 is on. So if you see what is the Z gate matrix corresponding to this, 1 0 0 minus 1, and I told you first column is off, second column is on. So here we have second column 1 minus 1. So that's why this 1 converted into minus 1. Okay, take the third one. The target is 1 0. Okay, so in the decimal state notation I can write it as a 2. So let me construct the oracle. So here as usual I'm taking this control Z gate, and if you see LSB here, the starting one 0. That's why here X, here X, and here also X. And the next one is 1. That's why nothing, leave it. So this is nothing but here control only, and X Z X. So that's why we can write this as some unitary operation. Just I'm taking like this. I hope you know here this is a minus 1 0 0 1. The diagonal elements of Z will interchange. Okay. So this operation is represented by, this is a 1 and a 2. Here control operation is there, and I told you how to write this notation. Z of, sorry, it's not a Z, let it be U, some unitary operation. U, it's a control, so control gate. Then C comma C plus T, I hope you know that. So 2 comma 2 plus 1, which is nothing but 3. So this is off and on. First column is off, second column is on. That's why 2 is nothing but -2, because of this first column we have -1. My humble request, if you are not understanding this, I request you please go back and watch this quantum circuits video, how to solve any quantum circuit by using decimal state notation. Lot of examples, lot of quantum circuits I have explained there, so I request you please watch. And the next one, fourth one, t equal to 1 1, right? So here, so as usual, this control jet gate is as usual, and here we don't have any 0, so that's why no Pauli X gate, so leave it. Then this is nothing but 1 and 2, it's a CZ operation, so that's why Z of 2 comma 2 plus 1, that is a 3. So this is off and on. So here I hope you remember what is this operator, 1 0 0 minus 1. In our method we have already explained first column, and this is the second column on. So here 3 will become -3. That's it. So these are the oracles for 2 qubit examples. Let us take a 3 qubits. Okay. Now I'm taking 3 qubit examples. Okay. So let us suppose the target state is 101. Let it be 5 in the decimal state notation with the 3 qubits. Okay. So just to take 3 qubits. Now first initially take all control operations and Z here. The last state you please take a Z. That means a C square Z. And after that please check where you have zeros. 0 is in the middle. So that's why here X and here X. So this one is nothing but here control, here anti-control, and here Z as usual. So I have already explained how to solve these quantum circuits 1 to 4 decimal state notation. Control means you just add that this decimal state, and anti-control don't consider that too. So let me explain. So here 4 is control and 1 is a target. So that's why this is a Z of 4 comma 4 plus 1, because a C comma C plus T. So here target is 1, that's why it is a 5. Okay, lot of examples I have explained. I request you please watch. And this is off and this is on. Okay, and Z, you know, 100 minus 1, that's why on state will get a phase change -5. Let us take one more. So let me take 110, that is a 6. Okay, so here we have, first please take all control, I mean C square, and here the last state as Z operation. And now, so where is the 0 at the last one? That means here. So here this is X and this is X. This is the starting and this is the starting one. Let's be 1 2 4 like this. Okay, so this can be written as, in our decimal state notation, how to solve this. Here we have two controls, but Since it is x z x, the unitary operator can be written as minus 1 0 0 1. So this is the control and this is also control. So this is a 1 2 4. Here we have z, sorry, not z, u, some operator, u of two controls are there. Whenever two controls are there, then what to do? Just add two control. That means C1 plus a C2 comma C1 plus a C2 comma, sorry, C1 plus C2 comma C1 plus C2 plus T. That's it. That means 4 plus 2 6, 4 plus 2 plus 1 7. It's a very simple algebra. Okay, off, first one is always off, second one is on. So here carefully see, here off and on. So 6 off, and here you have to take the first column for off state. That's why minus is there. So 6 will become minus 6. If you multiply, you will get the same thing. I mean matrix multiplication. But no need. Just directly you can do like this. Okay, and let me take a 4 qubit example also. 4 qubit example. Let me take one example. So here I am taking a target state as a 1010, which is nothing but a decimal state notation. It is a 10. So 4 qubits. So I have to take 4 qubit states. 1, 2, 3, 4. So control I have to take, another control, and the last one is Z. Right? Okay. And after that, please carefully see. First one we have a 0. That's why Pauli X gate here on both sides. Next one is 1, leave it. Next one is a 0, again take X gate. Here it is. And next again 1, then leave it. So I hope you understand. This is equivalent to, so here I am taking this unitary operator like this. Okay. And first one is control. Next one is anti-control. That means don't add that number. And this is a control. Okay, and here minus 1 0 0 1 x, some matrix x, then what will happen, the rows will interchange and columns will interchange from right side and left side. Then what will happen, once you interchange those rows and columns, so that diagonal elements will interchange. You need not to multiply, just leave it. So that's it. So this is 1 2 4 8. Now we have to add only control, that is 8 is control and 2 is control. 8 plus 2, 10, comma 10 plus target, target is 1, that is 11. So this is off, this is on, first column off, second column on. So that's it. So 10 become minus 10. That's okay. So like this we can construct the inversion operator. Okay, so here it is anti-control and here also some anti-control. I hope everybody understand how to construct this oracle corresponding to the inversion operator, which invert the amplitude of a target state. Okay. Next, we'll discuss about diffusion operator. Right. So now let us discuss about this diffusion operator. So the diffusion operator is a minus hn I naught hn. Okay. So let me explain this. So for example, here we have psi naught and this IT operator is operated, then we will get alpha naught summation remaining, this is state sum of all remaining states. The amplitude is inverted, that is the target state amplitude is inverted. Okay, so of course R is not equal to T. Now after this we are operating this diffusion operator. In the diffusion operator, forget about this minus. I have already explained in the earlier lecture what is this minus significance. Here the head mod gate operation is there. So once you operated this head mod gate, this is quite interesting. What will happen, So here already we have the phase, I mean the amplitude of target state is uh, target state become negative. Now once you operate this head mod operation, the amplitude of zero state will be increased by n minus 2 times, capital N minus 2 times. In the example you will understand more clearly. And the remaining states amplitudes become 2 times. Capital N is very large actually. That's why the amplitude of that zero state, first zero state amplitude is increasing. That's the beauty. So here, after this head mod operation, the amplitude of zero state is increased by n minus 2. Okay, and the amplitude of other states uh, increased by either positive or negative, just multiplied by 2, something like that we will get. That's why I'm using the word increase. If it is a negative side increase. If it is a positive side increase. Increase it by 2 times, exactly 2 times. For example, if you have 2 qubits, then capital N is what? 4. So then after this head mod operation, the amplitude of the zero state will be increased by 4 minus 2, 2 times. Okay, right. And after that, next one, phase oracle we are using. Phase oracle. So what is this minus sign? I have already explained. Actually, we would like to invert the amplitudes of the states other than 0. But in the formula we have I naught, which invert the amplitude of 0 state. Actually, this step is very crucial. You please tell me what is our final aim to get the target. So here what will happen, after applying this phase oracle, the phases of the states will be changed. Which states? Other than 0 states. Why 0 state is not changing here? Because already it is having more amplitude. That is also very crucial. So the remaining states of phases are changed, are inverted. If it is a plus, become minus. If it is a minus, it become plus. What will happen after this? So very important. So here um, amplitudes of states other than 0 are inverted. Okay, so after this what will happen, you will get some states. Here you will get a 0 to n minus 1 states, superposition of 0 to n minus 1 states, plus this is 0 state. Some amplitude will be there. Okay, so carefully observe. Now the beauty is, why we have inverted these amplitudes, this is exactly same as this one. We have superposition of 0 to n minus 1 states. This is exactly matching with H tensor n operates on target state. For example, target state is a 5. Okay, so H, uh, of course 5 means we have to take a H 3 times we have to operate. H tensor 3 operates on 5. Then you will get some phases of 0 state, 1 state, 2 state, 3. I'm talking about the decimal notation. Those phases and here whatever the phases you are getting, both are same. You will understand this point. Just remember this, and after this I will explain one example. There you will understand more clearly. So one more time, let me explain. We have already inverted the amplitude of target state and a diffusion operation started. In that first step is head mod. Why you are operating head mod? To increase the amplitude of 0 state. This is very useful. Just wait. Okay. and the remaining states also increase a little bit, actually not that much, a little bit. After that, you have taken one phase oracle which invert the amplitudes of other states, I mean states other than 0, then exactly you will get the situation. So you have superposition of 0 to n minus 1 states whose phases are exactly matching with this one. Then I hope now you understand. Again, one more head mod operation is there. So once you operate one more head mod, and what you will get, a target state. So here some amplitude will be there, here you will get some amplitude, that too more high amplitude. And you got a doubt, what about this? No issue, again you will operate a head mod and this will create the superposition state again. So that is a 1 over root n summation over x. Okay, so here already target state is there, here also target state is there, and again if you take common, the amplitude of target state will be increased. Earlier video I told you one point, after this diffusion operator no state will get a negative phase, because here all phases are plus only, positive. That means phases means that all are plus, no negative amplitude. That's it. And once you take in the common, so this you will get the target state with the high amplitude, with the high amplitude plus summation this remaining states with the low amplitude or less amplitude. That's it. So this is the diffusion operator. Okay, let me explain how to construct this for 2 qubits, 3 qubits and 4 qubits. It's easy only, no need to worry. Okay, so first I am taking a diffusion operator construction for 2 qubits. Or let me take this 2 qubits. So here diffusion operator D is equal to minus Hn I naught Hn. Okay, so 2 qubits states we have taken. Here I naught, I hope you know what is this I naught. This is already we have discussed here, this one. Okay, so control Z, and left side and right side we have Pauli X gate operations. This one already we have discussed, which invert the amplitude of 0 state only, right? And after that, so we have this head mod operation, 2 head mod gates, and here also we have head mod gates like this. That's it. Okay, and this is equivalent to, we can write like this also. So here I can take this anti control if you want, otherwise if you understand leave it, no issue. And this is a minus 1 0 0 1, that means always it will invert the amplitude of a 0 state only. Okay, and after that as usual here head mod. That's it. Okay, and let me take a 3 qubit example. And remember, so in this quantum circuit we cannot show this minus sign. That's why final answer, once you make a measurement, you will get one extra phase of pi. So your answer will get extra phase of pi, that is minus will come, right? And here also let me take 3 qubits states. As usual, first we have to take control and c square operation, and this is z. Okay, control z operation. And after that, on both sides we have Pauli x gates. So this is I naught. I naught means which invert the amplitude of 0 state. And after that, head mod gates. That's it. Okay. That's it. And if you want a 4 qubits, I hope you understand. This is easy only. If you want, you can write it as anti-control. Otherwise, leave it. No issue. So control, and here. And after that, on both sides, we have Pauli X gates. Sorry. That's it. And after that, head mod gates. That's it. Okay. So right, like this, we can construct the diffusion operator. But it's okay. But I hope you understand what is the importance of this diffusion operation. Okay. So this one, I request you please go through this. Then you will understand more clearly what is this Grover's algorithm, how we are getting the amplitude of a target state is increasing. But in the example, you will understand more clearly. So I request you please watch that next lecture also. Okay, I will explain 2 qubit example and a 3 qubit as well as a 4 qubit also. I will explain. Okay, so thank you. We will meet again.